Hi, I'm Bridget Norman, a system engineering student and a team lead for Team 21039. Our project is the Public Outreach Radio Telescope sponsored by the Steward Observatory. My team members include 2 mechanical engineers, Jared Northrup and Elizabeth Martinez, 1 optical engineer, Mason Veruso, and 2 electrical engineers, Shingri Zhang and Carrie Stoll. Our team was tasked with designing a radio telescope which will be accessible to U of A students, faculty, and members of the public, nicknamed the Port. The goal of this telescope is to teach the public about radio astronomy through hands-on experience. Radio telescopes have been responsible for some amazing astronomical discoveries. Some great examples such as the Event Horizon Array imaging the first ever black hole are shown on the screen. Our telescope with a 2.4 meter dish is smaller than these telescopes, but it will be able to show the public what the sun, moon, and other large celestial bodies look like at radio frequencies. Our telescope, shown on screen, was designed with performance, ease of use, and safety in mind. We were tasked with designing a 2.4 meter off-axis radio dish, and this dish had to be capable of connecting to an old LAZ mount that was supplied to us by the Steward Observatory. Our project scope was to design this new dish and provide a quote to our sponsor so he can construct a dish and truss structure over the summer of 2021. The scope also included the mechatronics and GUI necessary to control the telescope. Through this video, we hope to show this team's process and success in designing the Public Outreach Radio Telescope.
There were many design decisions over this past year that led to our final product. The first decision that drove our design was the need for a paneled radio dish that makes the 21 centimeter observation wavelength possible and displays our sponsor's novel panel forming technology. The second major decision was using an already existing alt-az mount for the base of our telescope, which saves time and money. The combination of these decisions greatly affected the design of the dish and steel backing structure. The choice to revitalize the old mount also dictated the GUI and electrical design. In order to end with the best possible design, an iterative engineering process was used. Analysis and testing was supported with constant research and professional feedback. Analysis was done on the old mount and the newly designed dish to assure system requirements were met. Prototyping and testing were done to revitalize the old mount equipment and simultaneously build the GUI. This iterative process was essential to the success of our project because the team faced many unexpected challenges that led to many major and minor system redesigns. Thanks to our rigorous engineering process, a final manufacturable design was reached. Shown here is a simulation of what our telescope will look like when tracking celestial objects once it is constructed by summer's end 2021. Zemax and GRASP were used to model and tolerance our system. Shown here are the system requirements met by our design. Once the optics were designed, mechanical analysis was conducted.
For the design of the truss and dish structure, the most critical system requirements were dish deformation and factory safety under operational and survival wind speed conditions. As with the FEA for the mount, fixtures, contact sets, and connectors were implemented to represent the system accurately within the simulation. At survival wind speeds and stow position, the system was subjected to gravity load and wind pressure loads found using SolidWorks flow simulation. The system was tested at different wind angles in order to determine the worst-case scenario under survival conditions. Meeting the factor of safety required several design changes, such as optimizing the truss structure to reduce weight. As you can see, the final design passes the 5-factor safety requirement at survival wind speeds. To analyze RMS deformation, 2 simulations were run subjecting the system to only gravity loading at zenith and horizon, and 2 simulations were run subjecting the system to gravity and operational wind speeds. The wind pressures were found using SolidWorks flow simulation, and the worst-case wind angles were used as the upper bound for RMS deformation. At the worst-case position for operation, the dish meets the 200 micron RMS deformation requirement.
For the existing mount FEA, we modeled it on SolidWorks by adding fixtures and contact sets to better represent the model as it underwent 3 main simulations. The purpose of the first simulation was to analyze the structural integrity of the mount under the weight of the dish system with no wind load. As you can see, the system met the factor of safety requirement. We then calculated the operational and survival wind loads on the mount, survival being the record high speed in Tucson using a MATLAB program. At the operational wind speed of 5 meters per second, the loads above the model were applied to the mount. The result for the deformation of the structure showed that the deflection from the loads only resulted in an approximate 1.94 arc seconds of pointing air. The final simulation represented the 25 meters per second survival wind speed forces exerted on the mount when the dish is stowed. The resulting minimum factor of safety for this analysis is 11.28, passing our 5-factor of safety. An analysis on the aluminum altitudinal axle confirms that any moments would not shear the axle under brake.
After performing numerous revisions, our finalized electrical design meets all the requirements and ensures the operation of the radio telescope is both safe and user-friendly. The power supply subassembly is responsible for safely delivering power to the all AZ servo motors. The power supply components are housed in the electrical cabinet we built. A lockout tagout standard safety practice was implemented into our design. To the right is an emergency stop button that interrupts the power when pushed. The mount's original servo motors and limit switch are powered by a single 800 watt power supply we repaired. Prototyping and testing was done to assure the components function and meet the power draw requirement. Given that the radio telescope will be mounted on the roof and be operated remotely, we designed to use 2 computers to tackle this challenge. One computer is installed in the operating room and runs the GUI, while the other computer, a Raspberry Pi 3, is installed on the telescope and runs the control software. 2 computers communicate via Ethernet for fast and easy deployment. The Raspberry Pi 3 controls 2 servo motors directly via RS-232. Both the control software and GUI are written in Python. And Arduino Nano is used to control the brake system and provide ADC functionality for the anemometer.
Here we have the GUI, which runs on our desktop. Our system requirement stated that we needed to create a GUI that would control the port as well as be user-friendly. As you can see, the GUI has capabilities which include the enable, disable of certain controls. It also has an Alt-AZ coordinate entry, jogging features, and a system status section, which allows the user to keep track of important system settings. It also contains multiple fail-safes which ensure the user can stop the telescope at any time with a simple click of a button, as well as coded-in software which does not allow the telescope to move past its mechanical limit. Since this telescope will be placed on the roof as shown and will be used by both the public and the university, our top priority was to make it as safe as possible. As discussed previously, all of our mechanical requirements had a factor of safety of at least 5. Stowpins for the Alt and AZ are implemented to restrict the telescope movement when stowed as an extra failsafe. Multiple safety features were included in the electrical design as well. First, we made sure that our electrical boxes were NEMA rated and that there were no exposed wires throughout the system. We also created a lockout tagout procedure which would ensure that the port was de-energized when not in use. That way, if there was maintenance or anyone on the roof near the telescope, no one would be able to operate the system. We also included 2 emergency stops, near the telescope and 1 in the operating room. Furthermore, multiple failsafes were written into the GUI. This includes software that ensures that the telescope will not exceed its mechanical limit. Finally, the software will automatically stow the telescope when wind speeds exceed 5 meters per second.
From our analysis and testing, we are confident that the port will be safe and functional. Rigorous drawings have made the telescope buildable and it will be completed by the end of summer 2021. Our deliverables for the port project include an easy-to-use GUI that operates the telescope, an instruction manual, and a complete electrical subassembly. We will also provide a quote report for the dish structure detailing the best shop to fabricate the telescope.
The most surprising obstacle we faced was the lack of documentation on the original student radio telescope. From this, the team learned how to find missing details by conducting tests and analysis as well as provide better documentation for the future. Another important lesson learned was the difference between an ideal design and a manufacturable one. Finally, we learned industry standards and how to communicate as professional engineers. We would like to thank Justin Hyatt and his research team from Stewart Observatory for their help throughout the project. We'd also like to thank Gary Redford for his mentorship over the past year. Finally, we'd like to thank the University of Arizona for this exceptional engineering experience.